Today's guest is Laura Manenti. Laura Manenti is a postdoctoral researcher with an interest in dark matter and neutrino physics. From Beyond Media, I'm Felix Tuchinski, and this is Humanity and Beyond. All right, well, how are you doing today?
Good. Thank you. Fine.
My very first question for you was, where did you get the idea for the music videos, which I personally enjoyed watching quite a bit?
So the idea, so the first one we made was at CERN. So basically at CERN, there are two liquid argon detectors, two big liquid argon detectors, each using about 900 tons of liquid argon. And those are prototypes for the final detector, which will be in the US, in South Dakota, for detecting neutrinos. These two prototypes do not detect neutrinos. They detect charged particles that come from the beam at CERN. And one it's called single phase, protodune single phase, and the other one it's called protodune dual phase. And for the single phase, what they did was having a scientist recording. She went inside the cryostat and she played the cello, and they recorded that. I was like, oh my God, that's so cool. We should do something similar. But I don't play the cello. I don't play any instrument, actually. And so I thought, okay, let's do something fun. And so we recorded this, that was not too much dancing, but it was like this song called June, I think it was called, on the notes of Boom, Boom, Boom. And then when we came back the other time for the installation of like a thing that I had to install, I thought, we should do like something with, I love Lady Gaga. So I thought, okay, let's use poker face, but like dual face. And so we wrote the lyrics. I wrote the lyrics, and then I have this colleague at UCL, and she's kind of as crazy as me. And so we thought, okay, let's record it as well. And so we went to CERN, like kind of at late time during the day on a Sunday, so that no one could see us. But the idea was actually to have fun. I'm not sure if they are like educational videos, especially because like you kind of not really get the lyrics unless like you know about the experiment. But we had so much fun, and that's why we did them.
If anything, it taught me that scientists can have fun too. It totally destroys the stereotype of you guys are all stuffy nerds with calculators and pocket protectors. It's like, no, they like Lady Gaga too.
I'm glad.
Yeah.
And that like sometimes you can also, it's good not to take like yourself too much seriously. And yeah.
Yeah, especially when you're dealing with the existential dread of dark matter. Yeah. But yeah, so she was just like a friend of yours at work, or?
So her name is Anastasia, and we used to work together at UCL in London, and then I moved here 2 years and a few months ago, but we were still working on this project together at CERN, and so so she's a colleague and a friend of mine.
It must be difficult not being able to work with, because I saw one of your videos. You had interns all the way from like Texas, for example, and from out. Yeah, because you must be limited to the Eurozone right now.
Right now, okay, as you can imagine, the situation is not super easy. So Xenon is currently upgrading to its next phase, which is Xenon N-ton, where N stands just for a big number greater than 1, which used to be the other detector. Right. It's actually now that N is 8.4 tons of liquid xenon. And this year there was a delicate phase, which was basically the installation assembly of the new detector. And we managed to do that despite the pandemic. We started to fill our detector, and so now we are in operation mode. I mean, we're managing. Obviously, we cannot have like as many, especially students coming over, and especially from the US because of like restrictions, or I mean, even myself from the UAE. But since it's like hardware, you need people to be there. So there are currently people on site taking shifts, just in another way with more precautions. Masks or tests, etc.
So I was just wondering what you missed the most about like having that international interaction.
For Xenon in particular, it's not that like we meet like every day on a regular basis. It's more like I usually go to Gran Sasso like once or twice a year, and I was there in September, and there was still that interactions with the people on site. Interaction in the sense that, yeah, you have your colleagues there. Probably right now, the thing that I miss the most is, that I missed the most up until now was the possibility of like coming to the lab here at NYU in Abu Dhabi. We now, most of the courses are still online, but the students are able to come to the lab only in a limited number. And that was something that I missed, like the interaction with the students, because it's not the same on Zoom. And another thing that I think people miss, although it has its pros and cons like anything else, is like conferences. So all the conferences that were scheduled in 2020 and took place were shifted on online, so they were virtual conferences, which do work, and it's also cost effective, less CO2 emissions. You don't have to fly to the other side of the world, which is great. I have 2 kids, so it's much easier to like organize childcare if I'm not leaving the country. On the other side, though, I think that it's good to network among scientists, and that's done better in person. Which cannot, I don't know. I have also like great relationships with people and whom I work with that I met maybe only once, but like having met them that one time makes the virtual relationship much easier as well, because you know that person, because we're like human beings made of flesh. Many people did enjoy the virtual conferences, but like having everything online is not ideal. So I would say that we found out ways to do things online, which we could have done before, but we just didn't do them. And that's great. And as usual, like the truth lies in between the black and white. So probably like a middle way between the two, the in-person and virtual, would be great in the future as well.
So yeah, let's jump straight into the research-based questions. So my question was about weakly interacting mass particles. I of course wanted to ask interesting questions, and I mean it seems like we're talking to weakly interacting mass particles relative only to matter, and like the matter we're made of, if I have to specify, do these weakly interacting mass particles only interact with matter and, I don't know, for example, antimatter or any other matter medium, if that makes any sense? Or do we not know?
So the matter we're made of, like me and you, is electrons, protons, and neutrons, and that's it. Gotcha. So and then protons and neutrons are made of quarks and gluons. Fine. And then you have other particles in the standard model of particle physics, which we know very well, such as muons, such as the tau particle. And then every particle has its own antiparticle. So like electrons have positrons, muons have antimuons, and so on. WIMPs are a specific category of particles which still have to be discovered. So currently it's an hypothesis, and we're looking for them, but they're not being found yet. And WIMPs belong to this category of particles that can make up dark matter. So dark matter is a bigger problem. So dark matter is, I usually explain to the lay person like this. You are in a dark room, you walk from one side to the other, and you feel there is something in the room. You step across something, and you bump into it, and you're like, okay, so there must be something in the middle of the room. I can't see it because it's dark, but I can feel it because it hurt, and so I know it must be there. And that's exactly like how dark matter works. You see gravitational effects which you can't explain if not by saying there must be something like some matter, something with mass in the middle, but I just can't see it. So then you devise, you make an hypothesis of what that thing might be. So for example, I could say, oh, the thing in the middle of the room is, I don't know, my brother, okay? And my brother is a human being, and it emits
infrared.
And so I could detect my brother in the middle of the dark room by wearing infrared glasses, okay? So I make up, I invent a device that can see the thing that I'm thinking could be the thing in the middle of the room, right? But then let's say it's not like something which emits heat, then the infrared glasses are not going to help, right? So you have to think of something else, right? So, and that's exactly the same with dark matter. So then you say this dark matter is made of weakly interacting massive particles, WIMPs, okay? And so you think, okay, so if these WIMPs interact the way that I think they interact, then let's build an instrument that can see them. And so detectors are really the eyes that we don't have, right? So, but then if dark matter is not made of WIMPs, it's made of something else, your instrument is not going to help you detecting dark matter, because dark matter is simply not made of what you thought it's made of. So right now, it's been several years that the WIMP hypothesis, it's used to be, and it is a good one. So what we have done as a collaboration was building a detector, the eyes that we don't have to see the WIMPs. And this detector uses a technology which is called dual phase liquid xenon time projection chamber. And what it is, it's a tank filled with liquid xenon. Xenon is a noble gas which is present in the air, and if you liquefy the air, you get several. You liquefy gradually different gases. The most abundant is nitrogen, and liquid xenon. When it's cold, it's pretty much like liquid nitrogen, which like usually people have heard of liquid nitrogen because you can make ice cream out of with liquid nitrogen or other other stuff. But it's much warmer than liquid nitrogen, about 100 degrees Celsius warmer. So we fill this tank with this liquid xenon, and then we wait for particles to interact with the liquid xenon. They give off a flash of light and also some charge. And we detect that flash of light. We push that charge upwards. That charge, when it's moved upwards, it's extracted into a gaseous phase. It emits other light, and we also detect that light. And by detecting this light, we can tell something about the nature and the position of the interaction of that particle. But what it is, it's really a tank filled with liquid xenon you wait for stuff to interact with it, you detect the flash, and that flash tells you about the particle. Now, the reason these detectors, like any dark matter detector really, is placed deep underground, usually in mines or under mountains like xenon, it's because you want to have a shield from other more abundant and very highly interacting particles, such as, for example, muons. So you place the detector underground so that you have a natural shield. That's how it's done for xenon. It was done for xenon 1 ton, and now it's done for xenon n ton. Xenon 1 ton is located under a mountain in Italy called Gran Sasso. It's like kind of near Rome, like 2 hours drive from Rome. And xenon n ton, which is currently there, built and installed, is exactly in the same place. It was like an upgrade of the previous detector. And where do these particles come from? Well, we think that we are embedded in a halo of dark matter. Like all of our galaxy is like, you have to imagine like a fog, and this fog is dark matter, but we just can't see it. But the detectors should be seeing it. Now, xenon has run for several years. It started off with 10 kilos of xenon, and then 50, and then we had like 100, and then 1 ton, and now more than 8 tons. And so far, we have not detected dark matter. So there are 2 possibilities. One possibility is these weakly interacting massive particles interact very, 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 very weakly, to the point that our detector is not sensitive enough to detect them, to see them. And that's why we kept on upgrading our detector to be more sensitive. It's like you are in this dark room with like a very feeble source of heat, and if you have a crap like infrared camera, you're not going to see it. But if you have a super fancy infrared camera, you're going to see that source of heat, okay? And then the other option is that in the dark room, there is no heat at all. The thing you bumped into, it does not emit heat. And so you have to think of something else. It's like, that's not the nature of the thing you're looking for. And that's the same for WIMPs. So it might not be WIMPs, it might be something else. So these are kind of the 2 possibilities. Also, xenon 1 ton and xenon n ton can also detect particles which are not WIMPs, such as, for example, oxygens. So this was one of your questions. So
right.
Back in June, we published we released this paper, which so basically we saw an excess of events, if you want, an excess of flashes, if you want, and we investigated the nature of those events. And one possibility is that the excess of events is given by a yet undiscovered particle, which is called oxyon. Oxyons were hypothesized or like theorized to explain other problems in particle physics, but they could also explain dark matter. So dark oxyons are not WIMPs, they're other particles, but we can still detect them with our detector. So even if it's not WIMPs, it could be something else, but there are a few options that we can still detect with xenon.
We'll be right back. We just want to thank all our listeners, and especially our supporters. Without you, all this would not be possible. The absolute best way you can help us is by sharing us on social media. If you really like what we are doing, you can support us on Patreon. That's patreon.com/humanityandbeyond. How likely is it that you detect something that, I mean, it'd be it'd be one thing if it was WIMPs, it'd be one thing if it was axions. What if it was something you did not predict? Like even the Higgs, like a good example is the Higgs boson. It was predicted in the math like 50 years before it was found, before there was experimental evidence. What if you found something for which you had no explanation with this detector? What would be because obviously you have to be scientific about it. You can't just be, you wouldn't announce it the day of the discovery. What would be the process of that if it was just something unknown? If we had to like start from, like, we had to like take relativity and go that far back and rewrite everything.
So in a way, I think that unexpected is like, sometimes I think it's a misleading word in like the scientific field. Okay, so for example, okay, the Higgs boson was really not unexpected. Like it was theorized. They built like $1 billion particle accelerator to find it, and they found it. It was not unexpected. It was very much expected. And dark matter is very much expected. And it's actually unexpected in a way that we have not found it yet, or that nature is kind of deceiving us. This is, again, my opinion as a scientist. I would say that when investigating a natural phenomenon, your attitude must be positive. There must be something. If you start from there is nothing there, then it's very hard that you find something. Then there have been a lot of like serendipitous or like, yeah, out of serendipity discoveries in science, in medicine. But it's because you were looking for something and you found something else. For example, the excess that I was talking about before, these low energy electronic recoils excess that we found was in a way unexpected, but like we were looking for it, like we were looking for something there. Then once you find that, then okay, in this regard, the like theoretical physicists are really, really good to come up with like ideas to explain what you are observing. In a way, you don't expect something, but in a way, you were looking for it. So it's just that it doesn't fit your model, maybe, the way you theorized. So you have to adjust your model to explain what you're observing.
It's sort of like, instead of there being a whole nother function, it's, oh, this variable was a bit off from what we were expecting or something.
Yes, or sometimes it's even more than a bit off. It's like maybe it's another model. Okay. But like, I would say, I mean, or at least let's say like this, that when you build a detector, you invest money, energy, and time and effort into building something, because you think that you're gonna find the thing that you theorized, okay, that your model predicts. So that's your like positive attitude towards reality, and then it might not be what you thought it was, but like when you start like looking into something, you are expecting to see something, like you are looking for something specific. You're not just building something and then we shall see. I mean, the LHC in a way, or Atlas and CMS were built to find the Higgs boson the way the model described the Higgs boson. And then if it's not there, then you say, okay, maybe there was something wrong.
So other than that, what else has surprised you since you turned the detector on? Any like equipment or data related? Has there been any surprise? Like, maybe let's not use the word surprise anymore. Like, has there been any a differentiation from what you built the detector for?
I would probably say that so Xenon was mainly built to detect dark matter, but now we can do a lot more stuff than just dark matter. We can look for neutrinos, for example. I guess we will soon be able to detect the elastic scattering of neutrinos with the xenon atoms, I don't think that people would thought we would have been able to do that like 10 years or 20 years ago. So I think that the most surprising thing is that you built something very specific for like that type of particle, but it turns out that it's such an outstanding detector, such an amazing detector, clean and sensitive and very low radioactivity, that you can do other science. So I think this is probably the most surprising thing about xenon, I would say.
It's almost like the Hubble of particle physics.
Yes,
And
yes.
just a good finishing question. How do you feel about your work, just in general?
Just in general, oh my god.
If it's too, I can. I mean, how do you feel about your participation in this? How do you feel about your place in history? I guess just.
I don't know if it's the answer you were looking for, but like so okay, myself in particular, I have this sense. The more you move on, the more I have this sense of being inadequate, that like I don't know enough. And I think that maybe that's not for like all scientists, but I know quite a few. And there is also this like thing about imposter syndrome, especially in like the scientific world, and it's kind of saying like you are in that place, but you don't know enough to be in that place. And I think, and that's also true, for example, for English. I think that's a good comparison. English is not my first language, as you can probably tell, it's Italian. And like, I think that when I started to learn English, at the very beginning, maybe after like a year, I spent a year in the US when I was 18. And compared to the previous year, like I could, I don't know, listen to someone speaking English and I could understand it like as if they were speaking Italian, or I could listen to a song and I could understand it. And I was like, oh my God, I'm so good at English, right? And now I've been speaking English for, I don't know, more than 13, 15 years. And I'm like, oh, I'm never going to be like a native speaker. And that's kind of the same for physics, that like, I don't know, you are in high school and you understand stuff and you're like, oh my God, I'm such good like rocket scientist in a way. And then you start uni and you get maybe even good grades and you're like, oh my God, I'm so awesome. And then you do your PhD and you're like, oh, I don't know if I really get this stuff. And maybe you do. And so you feel like very confident. And so you have these up and downs. But like right now I'm at a stage that I'm like, it's exactly with my English that I'm like, I need to learn more. It's never enough. And then the more I'm now doing a postdoc and I'm like following several projects, and I feel I never have the time and the energy to follow everything perfectly. And then there is also another aspect of life that like you're not only a scientist, but you are like a person with like, I personally have a family and I have 2 kids. And so I also have to think about that and do stuff at home. But also like mentally, that takes quite a lot of effort. And so it's, how do I feel about my work? That in a way, I'm never enough. Time is never enough. And at some point, you kind of have to deal with that, you will never reach perfection. Maybe some people can, I just can't. But maybe some do. I don't know. But it's also okay. And it's also okay if you don't know something. And it's also okay if you don't know something, because there are people that know more than you do, and you can reach out to them. And that's the good thing, I think, about conferences or like in-person relationships. That like if you know people, you can contact them and ask them questions. And I could tell you many examples about that in my life. So and even in the Xenon collaboration, there are many people who have different talents, and that's also the good thing about like being like diverse. I think like diverse in the sense of like also intellectual diversity. It's a very good thing to have, or diversity in terms of abilities. One is good with hardware, one is good with software, one is good with theory, and you learn from each other. So I don't know if that answers the question. How do I feel about my work?
I never look for an answer. My goal is always to get great information, and that would be a perfect example. Because wow, that is a deeply personal and very interesting look at the life of a postdoc. Like wow, yeah.
So
no.
what do you study now?
Oh, I'm nowhere near that. I study business.
Okay.
So I'm nowhere near any of this field. I just please get smarter. Please continue to learn, because that means that we as a species all benefit, because the better you do with your particle detector, the more we understand about our universe. So that's always good. So I think you're doing a great job. But I'm a business undergrad, so I don't know what I would know about that.
I also, I my only experience with like business or economy, I did an internship at an investment bank firm during my PhD, and I actually thought that it's a pity that we are so confined in our majors in a way. So I don't know, like before doing the internship, I didn't know what the LIBOR rate was, or the Euribor, or how bonds work, and it's but these I also say like regarding like physics. I think it's good to have like an interdisciplinary attitude at university as well. Because we could learn so much. I don't know. I have these next to me. It's a 3D printed. It's part of a 3D printed enclosure for an experiment we're working on, and the guy that designed it has a very high sense of like aesthetics and design, which I think it's brilliant, even if you're doing physics. So I don't know. I think like nowadays we're missing that a lot, because like if you do physics, you only do physics, and if you do math, you only do math, and if you do business, you only do business. And I think like what you're doing, like podcast, and like you're not even into physics, and you're asking physics related questions. That I think that's great. And we should do more about that, especially for in outreach.
All right.
Well, okay, it's been a pleasure. Good night, sleep well, enjoy your online courses, I guess.
Yeah. Good morning. Enjoy your work at Xenon.
Thank you. Bye.
Bye.
Bye.